October 9th, 1941. Wright Field, Dayton, Ohio. Theodore E. Harold Barth stood beside a blackboard covered in ballistic calculations, facing a room full of skeptical Army Air Corps officers. The president of Carl L. Norden Incorporated placed a wooden pointer against a diagram showing a B-17 flying fortress at 20,000 feet altitude, its bomb bay open, releasing ordnance toward a precisely marked target below. "Gentlemen," Barth said, his voice carrying absolute conviction despite the doubtful faces before him, "with our bombsight, your bombardiers will be able to place a bomb in a pickle barrel from 20,000 feet. The claim seemed impossible. Dropping an object from nearly 4 miles up through constantly shifting winds, through air of changing density and temperature, from an aircraft traveling at over 200 miles per hour, and expecting it to hit a target measuring just 30 inches across? The laws of physics themselves appeared to mock such precision. Yet Barth spoke not merely from confidence, but from a calculated strategy of promotion that would transform one device into perhaps the most famous piece of military technology of World War II. The bombsight he represented, developed over 2 decades by a difficult Dutch engineer named Carl Norden, would consume over $1.1 billion in development and production, an amount rivaling half the cost of the Manhattan Project. Nearly 90,000 units would be manufactured. Bombardiers would swear solemn oaths to protect its secrets with their lives if necessary. Armed guards would surround it. Hollywood would mythologize it. And the entire edifice of American strategic bombing doctrine, the belief that wars could be won through precision daylight attacks on enemy industry while minimizing civilian casualties, would rest upon this single analog computer weighing 35 pounds. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The uncomfortable truth that would emerge only after hundreds of thousands of bombs had fallen on Europe and Japan was more complex than Barth's confident sales pitch suggested. The Norden bombsight was simultaneously a genuine marvel of mechanical engineering and one of the war's most successful propaganda tools, a device whose legendary reputation far exceeded its actual combat performance, yet whose existence shaped strategic decisions that would determine the course of the air war. This is the story of how one man's perfectionist vision of precision created a device that promised to make war more humane, and how the brutal realities of combat at 25,000 feet through clouds and flak and German fighters transformed that promise into something very different. It is the story of the collision between engineering idealism and battlefield chaos, between theoretical accuracy and practical impossibility, between what could be achieved on a sunny day over the test range at Dahlgren, Virginia, and what actually happened over Schweinfurt and Regensburg and Berlin. The journey to that moment at Wright Field had begun 21 years earlier on a different continent under very different circumstances. Carl Lucas Norden, born Karel Lucas van Norden on April 23, 1880 in Semarang, Java, had been raised in a world of Dutch colonial privilege that would shape his exacting, perfectionist approach to engineering. His father, Edward, a prosperous merchant, died when Carl was only 5 years old. His mother, Cornelia, returned with the family to the Netherlands, where young Carl received his primary education at Nijmegen and Apeldoorn. From 1893 to 1896, he attended the Royal Art Academy at Dresden, Germany, but recognizing that his family had already committed to supporting his older brother's artistic career, Carl made the practical decision that pursuing art would impose an unacceptable financial burden. In 1897, he apprenticed himself to an instrument maker in Zurich, Switzerland, learning the precision metalworking skills that would define his life's work. In 1900, he entered the Federal Institute of Technology in Zurich, the prestigious ETH Zurich, where he studied alongside another intense, driven, self-disciplined student named Vladimir Lenin. Both men shared an absolutist certainty about their visions, an unwillingness to compromise on matters of principle, and a conviction that the world could be reordered through the correct application of systematic thinking. Norden graduated in 1904 with a degree in mechanical engineering and immediately emigrated to the United States. arriving as part of that wave of technically trained European immigrants who would transform American industry in the early 20th century. He worked several jobs initially, struggling to establish himself, before landing a position at the Sperry Gyroscope Company, where he worked under Elmer Sperry himself on gyrostabilizers for United States ships. The relationship between the two men was predictably difficult. Both were engineering geniuses. Both were temperamental, stubborn, and convinced of their own correctness. Sperry disliked Norden's habit of smoking vile black cigars in the workshop. More seriously, Sperry proposed that Norden sign over all rights to his future gyrostabilizer patents to the Sperry Gyroscope Company, an arrangement Norden found completely unacceptable. In 1913, after 4 years of increasing friction and a final dispute over salary, Norden left to establish his own consulting practice. He named his firm, with characteristic modesty, the Carl L. Norden Company. Navy personnel who worked with him during World War I would give him a very different nickname. They called him Old Man Dynamite, a reference not to explosive devices but to his volatile temperament and explosive reactions when things did not meet his exacting standards. Contemporaries described Norden as self-centered, impatient, domineering, driven, abrasive, a perfectionist, and a man of the highest ethical standards. He saw himself not as an inventor, believing that only God could truly invent, but rather as a designer who took existing principles and refined them to perfection. His name did not even appear on the patent for his most advanced bombsight, despite being unquestionably its primary creator. Norden sought anonymity and worked best away from public attention, often returning to Zurich to work at his drawing board, while his business partner Theodore Barth assembled the models in New York. The catalyst for Norden's work on bombsights came in the aftermath of World War I. The conflict had demonstrated aviation's military potential, but bombing accuracy had been abysmal. Pilots and observers dropped bombs by eye, using simple timing devices or crude iron sights that amounted to little more than holding out your arm and using your thumb as a reference point. From slow-moving biplanes at low altitudes, some hits could be achieved through sheer volume of ordnance. But as aircraft grew faster, flew higher, and carried heavier loads, the problem of hitting specific targets became increasingly difficult. The ultimate World War I development in bombsight technology had been the course-setting bombsight, or CSBS, essentially a large mechanical calculator that directly represented the wind triangle using 3 long pieces of metal in a triangular arrangement. The hypotenuse of the triangle represented the line the aircraft needed to fly to arrive over the target in the presence of wind, a problem that had previously been mathematically intractable for pilots under operational conditions. The CSBS worked through careful coordination between pilot and bombardier. The bombardier would first measure wind speed using various methods, then dial that speed and direction into the bombsight. This moved the sights to indicate the direction the plane should fly to take it directly over the target with crosswind accounted for, and also set the angle of the iron sights to account for wind's effect on ground speed. Then, approaching the target, the bombardier would watch objects on the ground pass through the sight and give signals to the pilot to alter the plane's course and correct for all wind effects. Almost every air force in the world adopted some variation of the CSBS as their standard interwar bombsight. The United States Navy used a modified version known as the Mark III, but the CSBS had severe limitations that became increasingly apparent as bomber aircraft evolved. It required lengthy manual procedures to estimate ground speed. It worked poorly against moving targets like ships. Most critically, it demanded close coordination between pilot and bombardier, which became difficult or impossible in the large bombers being developed in the 1920s and 30s, where the two positions might be separated by 50 feet or more of fuselage. In January 1920, the Navy's Bureau of Ordnance contracted with Carl L. Norden to improve the Navy Mark III bombsight. The Navy wanted a gyrostabilized platform that would allow bombing from higher altitudes, and they wanted the ability to bomb moving targets, particularly enemy warships. This seemed an ideal match between the Navy's needs and Norden's expertise with gyroscopic stabilization systems. Norden threw himself into the work with characteristic intensity. His first efforts added gyrostabilization to the bombsight, along with a telescope to better sight the target and a means for providing flight directions to the pilot through a device called the Pilot Direction Indicator, or PDI. Early prototypes showed promise, but suffered from vibration problems, leveling difficulties, and reliability issues with the PDI. In 1923, recognizing he needed help with the business and production aspects of the work, Norden took on a partner. Theodore Harold Barth, a former Army colonel trained in chemical warfare techniques, brought complementary skills in organization, promotion, and dealing with military bureaucracy. While Norden worked at his drawing board, often in Zurich, Barth assembled models in his New York City apartment and handled negotiations with Navy procurement officials. The collaboration proved fruitful. Together, Norden and Barth formed Carl L. Norden, incorporated in 1928, with Barth as president and Norden as consultant. The assistant research chief of the Naval Bureau of Ordnance, Captain Frederick I. Entwistle, joined them shortly after the company's establishment, bringing insider knowledge of Navy requirements and procurement processes. All three men participated in bombsight design and shared patent rights, though Norden remained the primary technical innovator. Carl L. Norden, Incorporated, produced its first operational bombsight in 1927. The Navy completed testing of this device, designated the Mark 11, in October 1927. The results were mixed. The gyrostabilization worked, providing a steady platform despite aircraft motion. The telescope allowed better target identification than previous designs, but problems with leveling, vibration, and the pilot direction indicator limited accuracy. The design required further refinement. Bureau of Ordnance testing at the Naval Proving Ground in Dahlgren, Virginia, which had begun in 1922, continued through the late 1920s as Norden refined his design. The breakthrough came with the development of what Norden called the Mark 15, a substantially redesigned system that addressed many of the Mark 11's shortcomings. The key innovation of the Mark 15 was its tachymetric design, meaning it directly measured the aircraft's speed and direction relative to the ground, rather than estimating these values through manual calculation. Previous bombsights, including the CSBS and the Mark 11, required the bombardier to manually determine ground speed through lengthy procedures involving timing how long it took ground features to pass through the sight. This was time-consuming, subject to human error, and became increasingly difficult at higher altitudes where ground features were harder to identify. The Mark 15's tachymetric system used a sophisticated mechanical analog computer that continuously calculated the bomb's trajectory based on current flight conditions. As the aircraft approached the target, the bombardier would establish a rate by keeping the target centered in his telescopic sight. The bombsight's computer constantly recalculated the proper release point as conditions changed, accounting for wind drift, ground speed, altitude, and the ballistic properties of the specific bombs being carried. Most revolutionary was the bombsight's integration with a mechanical autopilot system that Norden began developing in parallel. This system, eventually designated the Stabilized Bombing Approach Equipment, or SBAE, allowed the bombardier rather than the pilot to control the aircraft during the final bombing run. The bombardier would rotate the entire Norden sight so the vertical crosshair line passed through the target, then engage the SBAE. From that point forward, the autopilot would guide the bomber to follow the course indicated by the bombsight, automatically correcting for drift and maintaining heading. This solved the coordination problem that had plagued the CSBS. The bombardier no longer needed to give verbal instructions to the pilot, who then had to translate those instructions into control movements while maintaining formation and watching for fighters and flak. Instead, the bombardier flew the aircraft directly through his bombsight, making minute corrections through his telescopic view of the target, while the mechanical autopilot translated his inputs into immediate, precise control surface movements. The Navy tested the Mark 15 intensively at Dahlgren through 1930 and 1931. In October 1931, they conducted a competitive evaluation, pitting two Norden bombsights against each other, the production model Mark 11 and the developmental prototype Mark 15. The older Mark 11 scored 23% direct hits. The new prototype Mark 15 scored 50% direct hits on the target, 50%. Under test conditions, half the bombs dropped using the Mark 15 hit the target directly. This represented a revolutionary improvement over any previous bombsight. The results were so impressive that the Army Air Corps, which had been watching Navy testing with great interest, immediately acquired rights to the newer Mark 15 design. This would become the famous Norden bombsight that would equip America's strategic bomber force. The Army Air Corps' interest in precision high-altitude bombing had been growing throughout the 1930s as part of a larger strategic vision. American military doctrine in this period focused primarily on defense of the United States and its possessions. For the Air Corps, this meant developing the capability to attack enemy shipping at long range from widespread land bases, an alternative to expensive aircraft carriers. The combination of the Norden bombsight and the new Boeing B-17 Flying Fortress presented what Air Corps planners believed was an ideal solution. Small formations of B-17 seconds, using their Norden bombsights from high altitude, could attack enemy fleets with precision while remaining above the effective range of shipboard anti-aircraft fire. The high altitude would also increase the aircraft's range, especially when equipped with turbocharged engines like the 4 Wright Cyclone 9 radial engines of the B-17. But as war clouds gathered over Europe in the mid-1930s, Air Corps thinking evolved beyond anti-shipping missions toward a broader strategic bombing doctrine. Senior officers, including General Henry Hap Arnold, began to envision precision daylight attacks against enemy industrial targets, factories, refineries, transportation networks, power plants that would cripple an enemy's ability to wage war without requiring massive ground invasions like the horrific trench warfare of World War I. This doctrine faced significant opposition both within and outside the military. Strategic bombing of industrial targets meant bombing cities where workers lived. Critics argued this was inhumane, that it would inevitably kill thousands of civilians, regardless of how precise the bomb sites might be. President Franklin Roosevelt himself expressed reservations about strategic bombing, having publicly condemned German and Japanese bombing of civilian areas. Air Corps leaders needed a way to convince military leadership, Congress, and particularly President Roosevelt, that strategic bombing could be made acceptably humane through precision technology that would strike only military targets while minimizing or eliminating collateral damage to civilians. The Norden bombsight became the centerpiece of this argument. Carl Norden himself was deeply invested in this humanitarian justification. A devout Christian, Norden believed that war and bombing were inevitable realities of the modern world. Rather than oppose them, he wanted to create technology that would make bombing as humane and precise as possible, directing destructive force only against legitimate military targets while sparing civilian lives. This moral dimension was genuine for Norden, not mere marketing rhetoric. He saw his bombsight as a tool for civilizing warfare, for imposing rational precision on the chaos of combat. Theodore Barth understood that this humanitarian argument was also extraordinarily useful for securing government, contracts, and appropriations. The pickle barrel claim, probably originating sometime in the late 1930s, became the centerpiece of Norden Company promotional efforts. At some point, Barth or company representatives began claiming they could hit a 15-foot square target from 30,000 feet. The pickle barrel imagery was even more evocative. A bombardier could drop a bomb into a barrel, measuring perhaps 30 inches across from an altitude of nearly 4 miles. These claims were, to put it charitably, greatly exaggerated. In 1940, the average score for an Air Corps bombardier was a circular error of 400 feet from 15,000 feet, not 15 feet from 30,000 feet. Under ideal test conditions, the best bombardiers using perfectly maintained Norden bombsights could achieve circular errors of around 75 feet from 20,000 feet, which was indeed astonishing for the era. But this was a far cry from hitting a pickle barrel, yet the exaggeration served its purpose. The Army Air Corps, seeking to justify expansion and ultimately separation into an independent air force, promoted the Norden bombsight's capabilities enthusiastically. The doctrine of high-altitude daylight precision bombing promised not only military effectiveness, but also moral superiority over the German and British practice of nighttime area bombing. American bombers would strike precise military and industrial targets in daylight when they could see what they were bombing, minimizing civilian casualties while destroying the enemy's war-making capacity. In 1941, as American entry into the war became increasingly inevitable, production of Norden bombsights accelerated dramatically. The Army Air Corps had been receiving small numbers of bombsights since acquiring the Mark 15 design, but now orders multiplied. The devices were extraordinarily complex for their time. Each contained over 2,000 precisely machined parts, including 18 gyroscopes, dozens of resistors and capacitors for the electrical systems, complex gear trains, bearings that required tolerances finer than a fine watch, and sophisticated optical elements. Manufacturing bombsights in quantity required skilled machinists, precision tooling, and exacting quality control. Each completed unit cost approximately $8,800 by 1942, equivalent to well over $100,000 in modern currency. The complete system, including the SBAE autopilot, cost $13,000 per aircraft, an enormous sum when B-17 seconds were being produced by the hundreds. Security surrounding the Norden became obsessive as production scaled up. The Navy had originally classified the device as secret in 1927, meaning disclosure would endanger national security. This was reduced to confidential, meaning disclosure would be prejudicial to national defense, in 1936, to facilitate development and manufacturing. Yet, despite the technical downgrade in classification, operational security remained extraordinarily tight. Bombardier trainees had to swear a formal oath to protect the Norden's secrets with their lives if necessary. Some units required trainees to take what became known as the Bombardier's Oath, a solemn promise that heightened the mystique and impressed upon young men the profound responsibility they carried. General Hap Arnold insisted that the bombsight always be covered from view when being transported between the bomb vault and the aircraft before and after each mission. Navy regulations specified precise procedures for destroying the bombsight to prevent capture. 2 rounds from a .45 caliber service pistol into the rate end mechanism and 1 round through the telescope. Later, special thermite incendiary devices were developed that would melt the bombsight into a useless mass of metal and glass. Factories producing bombsights and components required hundreds of guards working around the clock. Workers were sworn to secrecy. The complete design remained classified. No photographs were released to the public. Even America's closest allies, the British, were initially excluded from technical details about how the Norden functioned. This wall of security, combined with Bath's promotional genius, transformed the Norden into perhaps the most mythologized piece of military equipment of the entire war. Hollywood embraced the narrative enthusiastically. Movies showed brave bombardiers protecting the secret bombsight from enemy spies, heroically destroying the device rather than letting it fall into German hands. Magazines ran breathless articles about the super-secret weapon that would win the war through precision. Newspapers described it in almost mystical terms, as if the device itself possessed magical properties rather than being a very sophisticated but ultimately mechanical calculator. One particularly persistent myth claimed that the crosshairs in the telescope sight were made from blonde human hair, specifically from one particular young woman from the Midwest who had never cut her hair before donating it for this patriotic purpose. The story was entirely false. The crosshairs were actually diamond-etched glass, a far more precise and durable solution than any biological material. But the human hair myth persisted throughout the war and for decades afterward because it provided such a perfect emotional connection between the home front and the technical marvel winning the war. The truth about the Norden's actual capabilities was far more nuanced than the propaganda suggested, and military planners knew it. The device worked remarkably well under specific conditions: clear visibility, stable air, moderate altitude, no enemy action forcing evasive maneuvers, a bombardier who had extensive training, and a properly maintained bombsight with all components functioning within specification. Under those ideal circumstances, the Norden was indeed capable of extraordinary accuracy. Test drops at Dahlgren in calm weather demonstrated the 75-foot circular error that impressed Navy evaluators. But those were not combat conditions. Combat conditions meant flying at 25,000 feet or higher to stay above the worst of the German flak. It meant clouds obscuring the target. It meant sub-zero temperatures at altitude that caused instruments to malfunction and oils to congeal. It meant German fighters attacking the formation, forcing bombers to take evasive action. It meant flak bursting around the aircraft, creating turbulence and forcing pilots to jinx and weave. Most critically, it meant that to survive in defended airspace, American bombers could not spread out and make individual bombing runs as the Norden was designed for. They had to fly in tight defensive formations, protecting each other with interlocking fields of machine gun fire. Only the lead aircraft in each formation would actually use its Norden bombsight to aim at the target. When the lead bombardier released his bombs, every other aircraft in the formation would immediately release as well, dropping their loads in unison. This formation bombing technique, developed out of harsh necessity during 1943's terrible losses over Germany, transformed precision bombing into area bombing. The bombs scattered across a wide pattern rather than concentrating on the precise aim point. The Norden's theoretical accuracy became largely irrelevant when 40 or 50 bombers were dumping their loads simultaneously based on one bombardier's sighting. None of this was yet apparent in October 1941, when Theodore Barth stood before those Army Air Corps officers at Wright Field and made his confident claims. America was not yet at war. The B-17 seconds were still a relatively small fleet. The doctrine of daylight precision bombing remained untested in combat. The Norden's reputation rested on test results and promotional claims rather than battlefield performance. The officers listening to Barth that day likely had their doubts. Experienced airmen knew that combat never matched the test range, but they also understood that the Norden represented the best bombsight technology available anywhere in the world. German bombsights were comparable but not superior. British bombsights were simpler and less capable. Japanese bombsights were significantly inferior. If precision bombing was going to work at all, it would work with the Norden. So the Army Air Corps committed fully to the device, ordering production in massive quantities, training tens of thousands of bombardiers in its use, building hundreds of bomb vaults on air bases in England and the Pacific and North Africa, and constructing an entire strategic doctrine around the assumption that the Norden would allow devastating attacks on precise military targets while sparing civilian populations. The propaganda campaign intensified as America entered the war. The Norden bombsight was presented to the American public as a war-winning superweapon, a testament to American technical ingenuity, proof that American boys could fight cleanly and precisely, rather than engaging in the butchery of area bombing. It became a symbol of American moral and technical superiority, a machine that embodied the nation's values. What made this propaganda so effective was that it rested on a foundation of genuine technical achievement. The Norden really was a remarkable device for its era. Carl Norden really had spent 2 decades refining it to near perfection within the limits of mechanical technology. The bombsight really did work extraordinarily well under the right conditions. The problem was that combat almost never provided the right conditions. And when tens of thousands of bombardiers took their Norden bombsights into battle over Europe and Japan, when they tried to hit factories and rail yards and oil refineries, through clouds and flak, while German fighters tore apart their formations, the gap between promotional claims and brutal reality would become painfully, tragically clear. But that collision between promise and performance still lay ahead. In October 1941, the mythology remained intact. The Norden bombsight was America's secret weapon, the technological marvel that would allow precision strikes against enemy industry, the device that would help win the war while keeping American hands relatively clean. 50,000 bombardiers would learn to operate it. Nearly 90,000 units would be produced. $1.1 billion would be spent. And whether the device delivered on its promises or not, its existence would fundamentally shape how America fought the air war. For better and worse, From the first tentative raids over France in 1942 through the atomic attacks on Hiroshima and Nagasaki in August 1945. The Norden's legacy would prove as complex and contradictory as the device itself simultaneously, a genuine technological achievement and one of history's most successful propaganda campaigns, a tool that failed to deliver on its most extravagant promises yet still helped win the war through sheer persistence and overwhelming numbers. August 17, 1943. 27,000 feet above Schweinfurt, Germany. Second Lieutenant Robert Hughes pressed his face against the rubber eyepiece of his Norden bombsight as his B-17 Flying Fortress, Jersey Bounce Jr., shuddered from the concussion of nearby flak bursts. Through the 20-power telescope, he could barely make out the sprawling complex of the Vereinigte Kugellagerfabriken ball-bearing plants, through the industrial haze and smoke from earlier bomb strikes. Hughes had trained for 6 months at Midland Army Airfield in Texas, learning every adjustment knob, every calculation, every procedure for operating the 35-pound analog and computer mounted before him. His instructors had told him, repeatedly and with absolute conviction, that with the Norden bombsight he could hit a pickle barrel from 20,000 feet. Some had even administered the formal bombardier's oath, making him swear to protect the device's secrets with his life. But today, at 27,000 feet, with me, 109 fighters slashing through the formation and 88mm flak shells, creating black flowers of shrapnel-filled smoke all around his aircraft, Hughes was discovering something his instructors had never mentioned. The device that had worked so perfectly on the practice range in West Texas, dropping 100-pound concrete bombs onto white circles painted on the desert floor, was nearly useless under actual combat conditions. The flak forced constant evasive maneuvers. Every time the pilot jinked left or right, the gyro-stabilized platform tried to compensate, but the violent movements exceeded the system's ability to keep up. The industrial haze over Schweinfurt made it impossible to see individual buildings with the clarity needed for precision aiming. The temperature at altitude, 40 degrees below zero, had caused frost to form on the telescope optics despite the electrically heated blanket wrapped around the bombsight. And most fundamentally, Hughes wasn't actually aiming at anything. He was the deputy lead bombardier for the 381st Bomb Group, flying in the lead aircraft's right-wing position. His job was not to use his Norden to pick out specific targets and drop his bombs precisely. His job was to watch the lead aircraft and release his bombs the instant he saw the lead bombardier's load drop away. Formation bombing, developed out of desperate necessity during the past 6 months of operations, meant that only one man in a formation of 18 bombers actually aimed. Everyone else simply dropped when he dropped. The formation bombing technique had become standard procedure across the 8th Air Force by July 1943, because the alternative, individual bomb runs with each aircraft spreading out to give its bombardier a clear view of the target, resulted in catastrophic losses to German fighters. B-17 seconds could only survive over Germany by flying in tight defensive formations where their 50 caliber machine guns created interlocking fields of fire. But tight formations meant bombs scattered across hundreds of yards, rather than concentrating on the precise aim point the Norden was designed to hit. Hughes watched the lead aircraft through his chin window. When he saw the bomb bay doors open and the first bombs tumble away, he hit his release switch. 18 aircraft dropped nearly simultaneously. 150,000 pounds of high explosive and incendiary bombs fell toward Schweinfurt, scattered by the formation's width, by altitude variations, by slightly different airspeeds, by the vagaries of wind at different altitudes. Some bombs would hit the ball-bearing plants, many would not. The Norden bombsight, the device that had consumed over $1 billion in development and production, the super-secret weapon that would win the war through precision, had been reduced to little more than a very expensive stopwatch in the hands of all but a few specially selected lead bombardiers. The mission to Schweinfurt would go down in 8th Air Force history as one of the bloodiest days of the war. Attacking without fighter escort deep into Germany, the bombers faced sustained fighter attacks from the Dutch coast all the way to the target and back. Of the 230 aircraft dispatched on the combined Schweinfurt-Regensburg mission, 60 were shot down, 600 men killed or captured. Several hundred more bombers returned with battle damage. The loss rate exceeded 25%, and despite all those losses, despite the extraordinary courage of the crews who pressed on through the fighter attacks and flak, despite the Norden bomb sites in each aircraft, the results were disappointing. Post-strike reconnaissance showed that much of the bomb load had missed the target entirely, falling on residential areas or open ground. The ball-bearing production that was supposed to be crippled for months recovered within weeks. The precision bombing doctrine had collided with combat reality, and reality had won decisively. The statistics emerging from combat operations through 1943 told a story that contradicted everything the Air Corps had promised about Norden accuracy. Several studies examining actual bombing results revealed that as few as 5% of 8th Air Force bombs fell within 1,000 feet of the target. 1,000 feet, not 75 feet, the circular error achieved under test conditions, not the pickle barrel Barth had promised. 1,000 feet, over 3 football fields away from the aim point, and that was only 5% of bombs. The other 95% fell even farther away. The average error for 500-pound bombs dropped over Europe in 1943 was calculated at 1,673 feet over a third of a mile. Missions sometimes missed their targets by miles, quite literally. One raid on a chemical factory in Germany saw 90,000 bombs dropped over 22 missions, with only 10% hitting anywhere on the 757-acre target complex. And of that 10%, only 40% detonated. The factory was back in full production within weeks. The Army Air Forces had planned their entire strategic bombing campaign around the assumption that the B-17 had a 1.2% probability of hitting a 100-foot target from 20,000 feet. This meant that to achieve a 93% probability of at least one hit, they would need 220 bombers attacking the same target. This was considered acceptable, and pre-war planning had called for 251 combat groups to provide enough bombers to fulfill the comprehensive bombing plans drawn up before America entered the war. But those calculations assumed that combat would resemble the test range, that bombardiers would have clear visibility and stable air and time to make careful adjustments to their Norden sights, that aircraft could make individual bombing runs without being blown from the sky by fighters. None of those assumptions survived contact with German air defences. The first large-scale combat use of the Norden bombsight with its associated automatic flight control equipment occurred on March 18, 1943, during a mission to Bremen-Vegesack, Germany. The 303rd Bombardment Group dropped 76% of its load within a 1,000-foot circle, representing excellent accuracy by combat standards. But that was one mission, one group, under relatively good conditions. Wider inspection of missions over Europe showed that only 50% of American bombs fell within a quarter mile of the target. The problems limiting the Norden's effectiveness were multiple and interconnected. Cloud cover over northern Europe was common throughout the year, and when clouds obscured the target, visual bombing became impossible. Bombardiers trained to use sophisticated optical instruments to identify precise aim points could not bomb what they could not see. The 8th Air Force eventually adopted radar bombing as an alternative, but radar of that era was not a precision technique in any meaningful sense. It allowed bombing through clouds, but accuracy degraded significantly. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The German flak defenses forced American bombers to fly at altitudes between 23,000 and 30,000 feet to minimize damage from anti-aircraft fire. As altitude increased, flak accuracy decreased, but the difficulty of hitting a target from that height increased exponentially. Once released, a bomb would encounter changes in wind direction and speed at different altitudes, temperature variations, air density changes, all factors that sent it off target. Even slight damage to a bomb fin during storage or loading would mean a miss instead of a hit. At the higher altitudes forced by flak, bombing conditions diverged even further from the test scenarios used to validate the Norden. Most testing had been done below 20,000 feet, but at 25,000 feet or above, factors that could be ignored at lower altitudes became critically important. The shape and even the paint on the bomb changed its aerodynamic properties in ways nobody fully understood. Some bombs reached supersonic speeds during their fall, creating ballistic complexities that the analog computer in the Norden could not account for. The temperature problem proved particularly vexing. At bombing altitude in unpressurized, unheated B-17 seconds, temperatures routinely dropped to 40 or even 50 degrees below 0 Fahrenheit. The Norden bombsight, with its precision bearings and delicate mechanisms, was designed to operate at room temperature. Extreme cold caused lubricating oils to congeal, making the gyroscope spin irregularly or stop entirely. Moisture in the air froze on optical surfaces, fogging the telescope view at critical moments. The Army Air Forces purchased electrically heated blankets to wrap around bombsights, attempting to keep them warm enough to function. But the blankets only partially solved the problem, and many missions were flown with Norden bombsights operating outside their design specifications, producing correspondingly degraded accuracy. Maintenance presented enormous challenges. The Norden required almost constant recalibration to maintain accuracy. Rough handling during ground transport could damage the sensitive gyro bearings. A hard landing or severe turbulence could flat spot the gyroscope bearings sufficiently to require a complete overhaul. The complexity of the device, with over 2,000 precision parts, meant that maintenance required highly trained technicians working in specialized shops. The bomb vaults that were one of the most technically demanding ground support roles in the Army Air Forces. By late 1944, inspection revealed that up to 75% of some batches of Norden bombsights fell short of specifications, missing targets by 280 feet from 20,000 feet when specifications called for 50 feet. The gap between design, intent, and operational reality had become a chasm. Combat conditions also introduced human factors that test range training could never fully replicate. Bombardiers operating over Germany faced not just technical challenges but psychological ones. German fighters attacking the formation meant watching friends die in aircraft exploding all around you. It meant knowing that at any moment cannon shells could tear through your aircraft, that you could be the next fireball tumbling toward Earth with no parachutes emerging. The stress of combat affected performance. Hands that could make delicate adjustments on the practice range in Texas trembled when 88mm flak shells were exploding close enough to rock the aircraft. Concentration required to operate the Norden optimally became nearly impossible when Me-109 seconds were making head-on attacks through the formation at closing speeds, exceeding 600 miles per hour. And overarching all these technical and human factors was the fundamental tactical reality that formations of bombers could not survive individually maneuvering for precise bomb runs. They had to stay together. Formation bombing became the only viable technique, but formation bombing meant that the precision capability of the Norden was used by only a handful of specially selected lead bombardiers in each combat wing. The 8th Air Force developed specialized lead crews for this purpose. Each squadron selected its best bombardiers, along with the best pilots and navigators, to form lead crews. These crews underwent intensive training and flew only as leaders, never as regular formation members. Their tours were shortened by 5 missions in recognition of the additional responsibility. 2 specially designated B-17 seconds in each squadron were configured as lead bombers, equipped with every available device for accurate bombing. This system improved results compared to having every bombardier independently aim, but it also represented a complete abandonment of the original precision bombing concept. When 30 or 40 aircraft dropped simultaneously on one bombardier's signal, the bomb pattern scattered across the target area. Some bombs would hit the intended factory or rail yard. Many would not, falling instead on nearby residential areas, on workers' housing, on schools and hospitals and churches. The moral distinction that American leaders had drawn between precise military bombing and indiscriminate area bombing began to blur. American bombs were killing German civilians in large numbers, not because bombardiers were deliberately targeting residential areas, but because the combination of formation bombing, high-altitude operations, and the limitations of the Norden bombsight meant that bombs scattered across entire urban districts. The most optimistic official assessment, conducted after the war by the United States Strategic Bombing Survey, concluded that 31.8% of bombs dropped by the 8th Air Force from 21,000 feet hit within 1,000 feet of their targets. Other analyses suggested hit ratios as low as 5%. Even the optimistic assessment meant that more than two-thirds of bombs fell farther than 1,000 feet from the aim point, a circular error more than 13 times worse than what the Norden achieved on the test range. A particularly telling incident occurred during the Normandy invasion preparations. On D-Day, June 6, 1944, the 8th Air Force bombed German beach fortifications before the amphibious landings. Despite attacking static targets whose positions were precisely known, despite having overwhelming air superiority with no German fighters to worry about, despite using their Norden bombsights under relatively good conditions, the majority of bombs missed completely. The fortifications remained intact, leaving them for naval gunfire and the infantry to deal with at terrible cost. One pilot, describing an in-flight emergency during the war, reported ordering his crew to dump everything overboard to reduce weight. All the ammunition, machine guns, even the Norden bombsight, the pilot said, noting that Lieutenant Fitzsimmons took a great deal of pleasure tossing it out. The willingness and pleasure the crew took in disposing of the supposedly invaluable super-secret device revealed volumes about the actual respect aircrews had for its worth after experiencing its limitations in combat. Yet despite all these problems, despite the gap between promise and performance, the Norden bombsight was not a complete failure. It represented the best technology available to any combatant for high-altitude visual bombing. German bombsights were comparable but not superior, and the Germans never developed a long-range strategic bombing force that would have used them extensively. Japanese bombsights were significantly less sophisticated. British bombsights, particularly the Mark 14 developed for night bombing, were simpler and offered roughly similar accuracy under operational conditions. The Norden's true value lay not in hitting pickle barrels but in being good enough, when used by skilled bombardiers under reasonable conditions, to hit large industrial complexes with sufficient accuracy to damage them. A bombardier might not be able to put a bomb through a specific factory building, but he could usually put enough bombs somewhere on a multi-acre industrial facility to disrupt production. When this capability was multiplied across hundreds of bombers per mission, and missions were flown day after day, the cumulative damage to German industry became significant. The combined bomber offensive, the joint American daylight and British nighttime campaign, eventually did cripple German industrial production, particularly oil production in the final year of the war. But this was achieved through overwhelming numbers and persistence, rather than the surgical precision that pre-war doctrine had promised. The improved Norden M9 model, introduced in 1943, incorporated various refinements, including better stabilization and a glide bombing attachment that allowed evasive maneuvers during the bomb run. By 1945, as the Luftwaffe had been largely destroyed and flak defenses degraded, the 8th Air Force could operate at lower altitudes under better conditions. Bombing accuracy improved significantly, with up to 60% of bombs falling within 1,000 feet of the aim point, almost 4 times better than in the dark days of 1943. This improvement owed as much to changed combat conditions, particularly the dominance achieved by P-51 Mustang escort fighters, as to any technical improvements in the Norden itself. When bombers could fly lower without being shredded by flak, when they could make more deliberate bomb runs without German fighters attacking, when the war had already essentially been won, the Norden finally approached its theoretical performance levels. But by then, the strategic bombing campaign had long since abandoned any pretense of precision. Following the devastating losses of October 1943, the 8th Air Force had increasingly adopted British-style area bombing tactics. Large formations would fly over a city, the lead plane would signal the drop, and hundreds of tons of high-explosive and incendiary bombs would pulverize everything below, hoping to catch military targets in the general destruction. This was exactly the type of warfare that the Norden bombsight had been promoted as preventing, the indiscriminate area bombing that American leaders had condemned when Germans practiced it against London and the British practiced it against German cities. The Norden was supposed to allow clean, precise, morally acceptable bombing of military targets only. Instead, it had become a component in a campaign that killed hundreds of thousands of German civilians and destroyed dozens of cities. The uncomfortable question that emerged from this gap between intention and outcome was whether the entire precision bombing doctrine had been fundamentally misconceived. Air Corps planners in the 1930s had convinced themselves and others that technology could transform the nature of strategic bombing, making it precise and humane. They had been wrong, not because the technology was fraudulent, but because they had failed to account for the realities of combat operations. No bombsight, however sophisticated, could deliver precision when bombers had to fly at extreme altitudes through clouds and flak while under fighter attack. No doctrine based on individual bomb runs could survive when formations had to stay together for mutual defense. No amount of training could prepare bombardiers for the psychological stress of combat. The vision of surgical strikes against factories while sparing civilian areas had been a fantasy, though perhaps a necessary fantasy to justify the strategic bombing campaign politically and morally. Carl Norden himself remained largely insulated from these battlefield realities. He continued working on improvements to his design throughout the war, focused on engineering perfection and unaware of, or unwilling to confront how his device was actually being used. Theodore Barth continued promoting the Norden's capabilities, though by 1943 the security classification had been reduced to restricted, the lowest level, and in November 1944 the bombsight was finally displayed publicly. The security surrounding the Norden had always been somewhat theatre. The entire design had been passed to Germany before the war started. Hermann W. Lang, a German spy employed by the Carl L. Norden Company as a draftsman and inspector, had gained access to the plans in 1938 and hand-copied the blueprints during a visit to Germany. In 1941, Lang was arrested along with 32 other German agents in what became the largest espionage prosecution in United States history, the Duquesne spy ring case. He received 18 years in prison on espionage charges, but the damage, such as it was, had already been done. The Germans studied the Norden designs and concluded that while sophisticated, it was overly complicated and no better than their own Luftwaffe bombsights. Since German doctrine emphasized tactical dive bombing rather than strategic high-altitude bombing, they never developed the long-range bomber force that would have used a Norden-type system extensively. The obsessive security measures, the armed guards, the bomb vaults, the oaths, the instructions to destroy the device rather than let it be captured, all had served primarily to enhance the bombsight's mystique and maintain morale among bomber crews. Giving air crews something to believe in, a super-secret weapon that represented American technical superiority, helped sustain morale during the most dangerous missions of the war. The Norden became as much a psychological tool as a physical one. Over Japan, the B-29 Superfortress crews discovered new challenges that made the Norden even less effective. The jet streams over Japan, fierce winds above 25,000 feet that added as much as 250 miles per hour to an aircraft's speed relative to the ground, pushed the bombers over targets too fast for the Norden to compensate. Flying against the jet stream, speed relative to the ground became so slow that the aircraft were sitting ducks for anti-aircraft fire. General Curtis LeMay, commanding 21st Bomber Command in the Marianas, initially attempted to maintain the daylight precision bombing doctrine he had practiced over Europe, but results were poor, and Japanese industrial output continued despite the raids. In March 1945, LeMay made the controversial decision to abandon daylight precision bombing entirely in favor of nighttime incendiary attacks from low altitude. The massive firebombing campaign against Japanese cities that followed in the final months of the war systematically destroyed Japan's industrial capacity and killed hundreds of thousands of civilians. The Norden bombsights, when used during these raids, served primarily to help aircraft navigate to the correct city rather than to hit specific targets with precision. Ironically, The Norden's last moment of historical significance came when it functioned exactly as designed under ideal conditions. The atomic bombs dropped on Hiroshima and Nagasaki were delivered by daylight high-altitude precision drop using Norden bombsights. The B-29 seconds, Enola Gay and Bockscar carried specially modified Norden units. The bombardiers, trained to near perfection for these singular missions, dropped their weapons in clear weather against cities with no air defenses. The bomb dropped on Hiroshima missed its precise aim point, the Aoi Bridge, by approximately 800 feet. The bomb dropped on Nagasaki, where clouds forced a last-minute switch to visual bombing of a secondary aim point, missed by nearly 1.5 miles. Even under ideal conditions, even with hand-picked crews and unlimited preparation time, even when the target was an entire city, and precision was less critical than simply getting close enough, the Norden still could not achieve the pickle-barrel accuracy that had been promised. Yet these imprecise drops hardly mattered. The atomic bombs destroyed their target cities regardless of where they detonated. The Norden had become irrelevant, a mechanical calculator from an earlier era superseded by nuclear weapons that made precision unnecessary. After the war, the truth about the Norden's actual performance gradually became public knowledge. The Strategic Bombing Survey, examining the effectiveness of the entire bombing campaign, documented the gap between promised and actual accuracy. Post-war analyses by military historians and engineers assessed what the Norden had and had not achieved. The mythology began to unravel as classified documents were released, and veterans wrote memoirs describing their actual combat experiences with the device. Carl Norden died in Zurich, Switzerland, on June 14, 1965, having received numerous honours, including induction into the National Aviation Hall of Fame in 1994. He never publicly acknowledged the gap between his bombsight's capabilities and the claims made about it. Whether he understood how his device was actually used in combat, whether he recognized that the humanitarian precision bombing he had envisioned had become area bombing that killed hundreds of thousands of civilians, remains unclear. Theodore Barth's promotional genius had created a legend that long outlived the wartime necessity for morale and propaganda. Even today, decades after the facts became known, the Norden bombsight retains its reputation as a super-secret weapon that won the war through precision. The pickle barrel claim appears in countless histories, often without context or correction. The human hair myth about the crosshairs persists, despite being definitively disproven. This enduring mythology reveals something important about how societies understand and remember technological achievement. The Norden bombsight was genuinely remarkable for its era, a sophisticated analog computer that represented the cutting edge of mechanical calculation and gyroscopic stabilization. Within its design limitations, it worked as intended. The failure was not engineering failure, but a failure of imagination, a failure to understand how different combat would be from the test range, how impossible precision would become at 25,000 feet through clouds and flak with German fighters attacking. The $1.1 billion spent on the Norden program, half the cost of the Manhattan Project, purchased not precision but the appearance of precision. Not surgical strikes, but the ability to claim moral superiority over German area bombing, even while American bombs scattered across German cities, killing civilians by the hundreds of thousands. It purchased morale for bomber crews who believed they carried super-secret weapons. It purchased political cover for strategic bombing as a concept, and ultimately, it purchased enough accuracy, when multiplied across hundreds of thousands of bombing missions, to contribute to destroying Germany's industrial capacity and will to resist. The Norden did help win the war, not through the revolutionary precision that had been promised, but through incremental contributions that accumulated across 3 years of relentless bombing. The final assessment of the Norden bombsight must acknowledge both its genuine technical achievement and its profound limitations. It was the best visual bombsight of its era. It worked remarkably well under the right conditions. Skilled bombardiers using properly maintained Nordens could achieve impressive accuracy when circumstances permitted. But circumstances rarely permitted. Combat intervened, weather intervened, German defences intervened. The chaos and terror and confusion of air war at 25,000 feet intervened. The device that promised to hit a pickle barrel from 20,000 feet ended up, under actual combat conditions, missing targets by thousands of feet on average. The device that promised precision and humanity ended up contributing to the deaths of hundreds of thousands of civilians. The device that was supposed to revolutionize warfare through technology ended up demonstrating the limits of technology, the stubborn refusal of combat to conform to engineering specifications or doctrinal assumptions. In 1967, the Norden bombsight saw its final combat use. The Navy's VO-67 squadron used it to drop acoustic sensors along the Ho Chi Minh Trail in Vietnam, trying to detect North Vietnamese troop movements. It was a mission far removed from the strategic bombing of German industry that the device had been designed for, a utilitarian use of equipment that happened to be available rather than any vindication of precision bombing doctrine. By then, guided munitions, laser-guided bombs, and precision strike weapons were beginning to make visual bomb sights obsolete. Modern smart bombs, with guidance systems built into the weapons themselves, finally achieved the precision that the Norden had promised but could never deliver. A laser-guided bomb really could hit a specific building, a specific window, even a specific vehicle. The technological dream that Carl Norden pursued in the 1920s and 30s finally became reality in the 1970s and 80s, but through completely different technical approaches. The legacy of the Norden bombsight is thus deeply paradoxical. It was both a remarkable achievement and an expensive disappointment. It both helped win the war and failed to deliver on its central promise. It represented the best that mechanical analog computing could achieve, while simultaneously demonstrating why digital electronics and guided weapons would be necessary for true precision. Most significantly, the Norden story illustrates the dangerous seductiveness of technological solutions to moral problems. American leaders wanted to believe that technology could make war clean and precise, that bombs could destroy factories without killing workers, that strategic bombing could cripple an enemy's war-making capacity without the messy business of actually fighting on the ground. The Norden bombsight became the technological embodiment of that desire, the device that promised to square the circle of devastating enemy industry while maintaining moral high ground. The promise was false. War resisted being made clean. Bombs scattered despite sophisticated aiming devices. Civilians died despite humanitarian intentions. The gap between what was promised and what was delivered should stand as a cautionary tale about expecting technology to solve fundamentally human problems, about believing that the chaos of combat can be tamed through engineering sophistication. Yet for all its failures, the Norden bombsight remains significant as an artifact of its era, a symbol of American faith in technology and progress, a testament to what mechanical ingenuity could achieve in the age before digital computers and microprocessors. The device itself, with its gleaming brass and steel, its spinning gyroscopes and precise gearing, its optical telescope and analog calculator, represents a peak of pre-digital technology, the absolute limit of what could be accomplished through mechanical means alone. And perhaps most importantly, it represents the courage and sacrifice of the 50,000 bombardiers who trained on the device, who took oaths to protect it, who carried it into combat over Germany and Japan, who operated it under conditions its designers never imagined, who watched friends die in flaming aircraft all around them, who pressed on despite knowing that their supposedly super-secret weapon was not quite living up to its reputation. Those men deserve to be remembered not for the device's shortcomings, but for their extraordinary courage in the face of terrible danger. The Norden bombsight promised to let B-24 seconds and B-17 seconds hit targets from 20,000 feet with unprecedented precision. In combat, it delivered something far less spectacular, but perhaps more genuinely human, a useful but imperfect tool that worked well enough, in the hands of brave men, under terrible conditions, to contribute incrementally to eventual victory. That unglamorous reality, stripped of mythology and propaganda, represents the true story of how one engineer's impossible dream of precision encountered the chaos of war and discovered the limits of both technology and human capability. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.